Okay, I had meant to record this yesterday, but it had unfortunately slipped my mind, okay? And with that, okay, this is a Boyle's Law application. The reason I say that is Boyle's Law is considered with volume and pressure. Charles's Law is concerned with volume and temperature, okay? And then these bottom two are conversions that pressure has to be measured in atmospheres and temperature has to be measured in degrees Kelvin. And these are two different types of conversions that we would use to convert kilopascals to atmospheres and millimeters of mercury to atmospheres. Okay, and that's what you see right here. 101.325 kilopascals is 1 atmosphere. 760 millimeters of mercury is 1 atmosphere. So don't worry about this content over here. This is for the Chemistry 2 class and the Anatomy and Physiology class. Okay, but in this case, when a high altitude balloon is released from the ground, where the volume is 725 milliliters, at altitude the pressure is 25 kilopascals and the volume is 430 milliliters. What was the pressure on the ground? Okay, so for some of these, when we're dealing with Boyle's Law, I was explaining, I think they would do some testing on some high altitude balloons when we're overseas, just on account of what happens is as the pressure is going down, the volume is going to be going up in any type of structure. So what that means and why that's important is we can look at that as an inverse relationship, okay? So for instance, in Boyle's Law, if the pressure is going down, well then the volume is going to be going up, okay? But that's not the case when we look at Charles's gas law. For instance, if you park your car in the garage where it's nice and heated up, and we're going to say it's 70 degrees when you leave your residence and drive to school, where it's maybe 5 degrees outside. I mean, the volume isn't going to change much in your tires, but it's probably going to go down just a little bit. The temperature's going down, okay? Temperature's going down, so the volume's going to go down just a little bit. Then when the temperature goes up, well, then the volume's going to go back up again. And it's not quite a big difference, but that's how you would interpret Charles's gas law. But with Boyle's, if one's going down, the other one's going up. And one of the things that, or aspects we tried to explain in class yesterday was think of it this way. This is a valve inside of your vehicle. And of course, inside of there, you're going to have this piston. And then the idea is it's attached to the crankshaft down here. So what's happening is as that piston is going up, okay, well, going from here to here, okay, that's getting smaller and smaller and smaller in area. So therefore, you would say the volume is really going down as that piston's going up, okay? So the volume's decreasing, okay? The piston's moving up. So what's happening to the pressure? Well, that's going to start to increase, okay? Then after the spark has ignited in the cylinder, well then what's going to happen, okay, I want to keep these on the same side, okay. So then once this is going down, look at all this space that you have in here after that spark has ignited. Well, the volume is really going up. It's starting to increase while the pressure then is going to start to decrease, okay? So hopefully that's a good application that you can look at that when pressure is going up, the volume is going down, okay? And then if the volume is going up, well, then the pressure is going down. That's what's happening inside the cylinders of your vehicle. Now, for some odd reason, should there be a little gap in your cylinder, then you're going to start to lose compression. Of course, that's really going to change, especially with that of the pressure. Rather than getting all of that force to push down, you're just having hot gases escape. So that's why important to have lubrication in your cylinders, or, of course, oil. All right, so with that, just like with any physical science problem, we would say, okay, you've read the problem. The next best thing that you can do is write down the information that you know. And in this case, volume either has to be measured in liters or milliliters. You don't have to convert them unless you're asked to do so. If you want this in liters, that's fine. You would just divide by 1,000 and get 0.725 liters. Divide by 1,000, 0.430 liters. You can do that at the beginning or the end of the problem because it's just moving by a power of 10. Okay? But the pressure, again, has to be in atmospheres. But, okay, on the ground, the volume was 725 milliliters. So that's our initial conditions. 725 milliliters. Okay? Then, at altitude, I mean, this balloon is attached or tethered to the ground, where all the way up there, maybe 500 feet, something to that effect, the pressure is 25 kilopascals. Okay? And then, oops, I goofed because it says what was the pressure on the ground. Okay? Up at altitude, that's where this number goes. Okay? And the volume was 430 milliliters. Okay? So then it goes on to say, what was the pressure on the ground? Well, we don't know. But once you have this information down here, you don't have to continually look up in the problem where that information is located. You can just look down here at your setup, but make sure you change that to atmospheres. And just like doing molar mass problems, this was measured in grams, the next step that you would do, you'd want grams on the bottom. But in this case, our conversion factors to cancel kilopascals is to put that down here and then atmospheres up here. And what we showed earlier is that for every 101.325 kilopascals, you're going to get 1 atmosphere. So then dividing these two, okay, 25 divided by 101.325, and that gives you approximately 0.25 atmospheres, okay? Because these have to be measured in atmospheres. Now we can proceed, okay? And then we can use our Boyle's Law application, okay? And in this case then, just do what the formula tells you to do. Volume 1, okay, 725 times pressure 1, but we don't know that because we got a question mark here, equals, okay, our second pressure times our second volume. Well, we converted kilopascals to atmospheres, so we've got 0.25 times 430, and then you multiply those two, okay, and in this case, 0.25 times 430, not 460, okay, gives us 107.50. What did I say, 107.5. Of course, get pressure 1 by itself, divide each side by 725. Okay, so pressure 1 equals 0.14 atmospheres. Okay. .15. Okay. All right. All right, so that's what we did yesterday. We'll have a paper. I'll email that to you, and then we will move on from there. All right, that's all I have. We'll catch up to you next time.